I'm a technical advisor for QC Ware and also a postdoc at UC Berkeley. And today I'll be telling you about the landscape of quantum algorithms, just giving you a very high-level overview of what's happening in this field. So the goal of this talk is threefold. First, I want to explain to you the very basic concepts of quantum algorithms, namely the notion of quantum speedups and how we quantify these as computer scientists and kind of what they mean from a business perspective. The second is to introduce you to the basic algorithms for optimization. You may have heard of this thing called the QAOA, or the Quantum Approximate Optimization Algorithm, so I'm going to tell you about that. And I'm also going to introduce quantum algorithms for chemistry problems. Namely, you might have heard of this algorithm called the VQE algorithm, or Variational Quantum Eigensolver. So I'm going to explain what that is and what it potentially means for businesses. And the audience of this talk this is intended for a business audience, but I'm happy to field either business-related questions or technical questions kind of as we go along. And while I should just say something that while I'm going to focus on optimization and chemistry problems, there's actually a much wider universe of quantum algorithms that exist. So for instance, there are quantum algorithms for cryptography, such as Shor's algorithm, which breaks many public key crypto systems. There are also algorithms for certified random number generation in the cryptographic space. There are quantum algorithms for differential equations, like for instance, for applying to the finite element method. And there are also many quantum algorithms for machine learning as well. And Jordanis Karanidis will be covering this in the next talk. But today I'm just going to focus on optimization and chemistry. All right, so let's start with the basics of quantum algorithms. So the reason that it's very important to study quantum algorithms is that quantum computers are only better at solving certain computational tasks than classical computers. So they don't speed up all computational tasks. They are only better than classical computers at specific problems. So this is why it's very important for us to understand which problems quantum computers will be better at solving and to what extent they will be better at solving them. So the way that we study this is by classifying quantum speedups. And the way that we classify these speedups is by how they scale as the size of the problem grows. And the reason we do this is that this gives us some sort of ballpark estimate of how big the speedups will be as quantum hardware improves and can solve larger and larger instances of these problems. So the other reason that we study the scaling is that this metric is hardware agnostic. So the scaling of the quantum algorithm will be the same if it's run on an ion trap or a superconducting processor or neutral atoms, etc. So it's kind of giving us a hardware-independent picture of what the capabilities of quantum computation are. So the way that we like to think about this is we like to make plots like this, where we plot the time to solution for solving your problem versus the size of the problem that you're solving. So let's say you have a classical algorithm that takes some amount of time to solve your problem of interest. Then we'll plot, the time to solution that the quantum algorithm takes to solve the exact same problem. And if the quantum algorithm has a faster time to solution than the classical algorithm, we'll call that a quantum speedup. And the amount of performance improvement is the kind of the way that we quantify the speedup here. Now, there are actually many different kind of flavors of quantum speedups that exist in the quantum algorithms world. So let's say that we plot the performance of some classical algorithm versus two different quantum algorithms. Some quantum speedups are what we call polynomial speedups. So what's a polynomial speedup? Well, technically it means that the runtime of the quantum algorithm is a polynomial in the runtime of the classical algorithm. And likewise, we define a notion of exponential speedups. And this is where the quantum algorithm exponentially outperforms the classical computer at this task. So on this picture, if you were to plot the runtime of an exponential speedup versus classical counterpart, you'd see the quantum algorithm's runtime is like almost flat. So what this means is that with exponential speedups, the quantum algorithm tends to pull away from the classical algorithm much more quickly and at smaller problem sizes than tends to happen with polynomial speedups. So this has important ramifications from a business perspective, because it means that exponential speedups, because they kind of kick in earlier in terms of providing large speedups, it means that they might be able to provide practical speedups even at relatively small problem sizes, and therefore with relatively small quantum computers. Now, on the other hand, polynomial speedups, they also improve over the over the classical performance, but they just do so a little bit more slowly than the exponential speedups do. So what this generally means, as a rule of thumb, would be that with polynomial speedups, they might require medium to large-scale quantum computers to be practically useful. The reason that we care about this so much is that currently quantum computing time is much more expensive than classical computing time. So as a result, it's kind of only commercially viable to run a quantum computation if there's really a substantial speedup to be found. So this is the way that theorists kind of view quantum speedups, classifying them into polynomial versus exponential speedups. But I want to emphasize that if you're a practitioner, you might not need to worry so much about this distinction, because both exponential and polynomial speedups can be useful from a practical perspective. So to make this concrete, let me describe a problem that has only a polynomial quantum speedup, and you'll see how big of a performance improvement it gets. So a classical example of a quantum speedup is for the problem of finding a needle in a data haystack. So let's say you have some giant database, and you'd like to search that database to find some item of interest. Now, if you have a database of, say, 1 million items, then the best classical algorithm to solve this problem is brute force search. It will take you roughly 1 million steps in order to solve this problem. But on the other hand, quantum computers can run an algorithm known as Grover's algorithm, which has a quadratic speedup, which is a particular type of polynomial speedup. And this algorithm would only take 1,000 steps to solve the same problem, because basically the runtime of the quantum algorithm is the square root of the runtime of the classical algorithm. So even though this is merely a polynomial speedup, if you are able to run it on this large of an instance size, it would have a very substantial performance boost. Okay. So there's another very important distinction to make when discussing quantum speedups and quantum algorithms, and that is to distinguish between heuristic algorithms and algorithms with provable performance guarantees. So some quantum algorithms that you've heard of have provable speedups. What do I mean by that? I mean that oftentimes one can mathematically prove or show that the quantum algorithm outperforms its classical counterpart. And these sort of provable algorithms really played a very important role, not only in industrial applications now, but also in the history of the field. Because long before people were capable of building quantum computers, scientists such as Peter Shor and Locke Grover discovered these provable algorithms existed just from a mathematical standpoint, and that's what kind of launched this whole endeavor of building quantum computers in the first place. But on the other hand, there's kind of another family of quantum algorithms that's been beginning to emerge in the last few years as quantum computers have improved in terms of their performance. And that is the development of quantum heuristic algorithms. So what a heuristic algorithm means is it means that there's no proof that this algorithm outperforms its classical counterpart. But oftentimes there is some intuition that there might be some speed up there. But there's no proof as to what the performance will be. Now, the important thing to remember when studying quantum algorithms is that all known quantum algorithms that we are capable of running on near-term devices are heuristic algorithms. So that is to say, we do not know in advance how these algorithms will perform. But on the flip side, these algorithms have this advantage that they can be run on relatively small system sizes. So we'll soon be able to test how they perform in the real world. On the other hand, all known quantum algorithms that have provable speedups, that is, with provable advantages over the classical counterparts, these require medium to large-scale quantum computers. In particular, most of them require fault-tolerant quantum computers or something very close to that. So these algorithms are really nice because we know exactly how well they will perform. They're going to very substantially outperform their classical counterparts. But the challenge here lies in the hardware. The challenge is to build better hardware to run them on. And there's also an algorithmic challenge to kind of decrease the hardware requirements of these provable algorithms in order to bring their speedups closer to the near term. Now, the fact that all these near-term algorithms are heuristic doesn't mean that they're not going to be useful. When theorists think about algorithms and proving performance guarantees, they usually demand that the algorithm works or succeeds on all instances of the problem. So let's say you were trying to study some routing problem on some graph of nodes. The theorist would usually require that the algorithm works on graphs that are very artificial or sometimes mathematically constructed to be difficult examples of the problem. But what happens in the real world is that people usually only care about the performance of these algorithms on very specific problem instances, namely the ones that they encounter in their business. So they might not care how some routing algorithm performs on this graph on the left, but they might only care about how it performs on the actual graph of, say, this is a flight network between US airports. And the interesting thing about real-world data is that there's usually much more structure or special properties of these real-world instances of problems that can make these problems easier for the algorithms to tackle. Now, this can be a double-edged sword because these same bits of structure can also make the problem easier for classical computers as well. But what I'm really trying to indicate here, though, is that the practical considerations for these algorithms are really a different game than the theoretical considerations, because here the game is really all about seeing how these algorithms perform on your data. So this is just to summarize that. If you want to understand quantum speedups from heuristic algorithms, you're probably going to need to try them on your actual data. Okay, great. So that's kind of the very high-level picture of the basics of quantum algorithms. So I'm now going to give you a brief overview of quantum algorithms for optimization problems. So I don't need to tell you that optimization is ubiquitous in industry, which we've had several nice talks about this kind of earlier in the day, both in routing and scheduling problems, and then financial problems such as portfolio optimization and derivative pricing. So today I'm going to describe two prominent quantum optimization algorithms, namely Grover's algorithm and something called the quantum approximate optimization algorithm, or QAOA. Now, before I move on to describing these algorithms, I just want to quickly point out that lots of other quantum optimization algorithms exist that I'm not going to talk about. For example, there are quantum annealing algorithms for optimization, which are some heuristic algorithms. And there's also quantum algorithms for these things called semi-definite programs, which have provable speedups over their classical counterparts, but more stringent hardware requirements. But today I'm just going to focus on Grover's algorithm and QAOA. Okay. So Grover's algorithm is one of the most famous quantum algorithms. It was discovered by Grover in 1994. And Grover's algorithm provides a polynomial speedup for optimization problems. The basic idea of Grover's algorithm is that the quantum computer can search through the extremely large list of possible solutions to your optimization problem much more quickly than a classical computer could. In fact, quadratically more quickly. And this algorithm is really nice because it has this very strong performance guarantee. That is, Grover's algorithm essentially is guaranteed to find the best possible solution to your optimization problem. The other advantage of Grover's algorithm is that it's very widely applicable to basically any optimization problem you can think of, such as database search, convex or non-convex optimization, integer programming, Monte Carlo methods in finance, you name it. It's actually proven in a very general black box framework. So Grover's algorithm comes up very frequently in algorithm design as a subroutine for many other quantum algorithms as well. But now the downside to Grover's algorithm is that this algorithm is not amenable to near-term quantum computers. nor can it be improved. So actually, even predating the invention of Grover's algorithm was a proof that no one could do better than Grover's algorithm. This was a result by Bennett, Broussard, Bernstein, and Vazirani in 1994. And subsequently, Zalka showed that this algorithm is really exactly tight. Like, it cannot be made lower depth. Even the constant in the runtime cannot be improved. The constant is something like pi over 4. So there's some like very nice numbers there. So what this means is that this algorithm is really great in terms of achieving long-term asymptotic speedups for quantum computers, but it's not something that we know how to implement on near-term devices. Nor is it something we would expect to be able to do so. So someone inspired by these limitations of Grover's algorithm, more recently, proposals have been put forward for algorithms for optimization that might be a bit more amenable to near-term devices. And the prominent example of this is the quantum approximate optimization algorithm, or QAOA. So the basic idea of QAOA is, instead of demanding that the quantum computer finds the best possible solution to your problem, like Grover's algorithm achieves, let's instead ask it to perform an easier task. Let's just ask it to find an approximately optimal solution. And in practice, usually this can be good enough for all practical purposes. And what's very interesting is that in 2014, Farhi, Goldstone, and Gutman showed that even noisy, low-depth quantum computation can find approximate solutions to optimization problems that might be much better than you would have expected before their paper. Now, I want to point out that this algorithm is a heuristic algorithm, so it does not have a provable speedup. And in fact, we know that on worst-case instances, we would not expect it to have a speedup. So at the moment, on all problems for which QAOA has been studied, it is beaten by the best classical algorithm on worst-case instances. But on the other hand, there is intuition that that QAOA could provide some quantum speedups from near-term devices. And the intuition here is really coming from the fact that there's some mathematical fact that the QAOA generalizes to Grover's algorithm as you ratchet up the depth of your quantum circuit. So you can think of the QAOA as a kind of weaker form of Grover's algorithm, which is much more localized in some technical sense than the normal Grover algorithm. And this localization is what makes this algorithm kind of intrinsically error-prone. So this is why this is often considered as a candidate for running on near-term devices. On the other hand, the localization aspect of this algorithm is also part of what makes it beaten by the best-case classical algorithms, because these tend to be algorithms that are much more global in nature. So the reason that people are very interested in QAOA, as I said, is that it seems to be implementable on near-term hardware. And because it's a heuristic, again, we'll just need to run it on actual data to see how it performs, and compare that with the best classical heuristics for the same problem. There's some emerging literature on the performance as well. Okay, so I'm just going to summarize. So Grover's algorithm delivers optimal solutions, but it requires fault-tolerant, large-scale quantum computers. So if you're looking for a kind of very hand-wavy estimate of how big of a quantum computer you'll need to run Grover's algorithm on a substantial problem size, you're looking at something like 1 million qubits or something. So this is not something that we're expecting to run on near-term devices. On the other hand, the nice thing about QAOA is that it can be run on these mid-sized devices. It doesn't deliver as good as solutions as Grover, so it only delivers approximate solutions. And it's a heuristic algorithm, so we don't know what the speedup will look like. But on the kind of advantage side is that the number of qubits you would need to run this on an interesting problem is maybe hundreds to thousands of qubits and reasonable fidelities. Okay, great. So that concludes the portion of the talk on quantum algorithms for optimization. I'm now going to give you the very basics on quantum algorithms for chemistry as well. So quantum chemistry is actually one of the original applications that was envisioned for quantum computers. So when Richard Feynman proposed the idea of quantum computers in the 1980s, the reason he proposed them is this observation that quantum mechanical systems and quantum chemical systems are very difficult to simulate with classical computers. So maybe we can use quantum systems to simulate these more efficiently, because in some sense, this is the native problem that quantum computers can solve that classical computers cannot. And there are many applications of this, from computing chemical properties to computing dynamics of systems like protein folding and catalyzation that were covered in the last talk. Now, there are two prominent quantum chemistry algorithms I'm going to tell you about today. The first one is Hamiltonian simulation, and the second one is the variational quantum eigensolver, or VQE algorithm. There are many variants of these algorithms, but I'm just going to try to describe kind of the space of these algorithms at a very high level. So what is Hamiltonian simulation? So Hamiltonian simulation is the problem of trying to simulate the dynamics of quantum chemical systems. So, for example, if you were to think of this in analogy to what people do in classical mechanics, like let's say you're building a bridge or something like this, the dynamics problems associated with building bridges are, say, in an earthquake, if you shake the bridge, how will it perform? How will it vibrate? So this is a question about how the system changes with time. And it's been known since the 1990s that quantum computers can efficiently simulate the dynamics of quantum systems. Now, the nice thing about Hamiltonian simulation is that we believe that this represents an exponential speedup over classical computing. The reason is that there is some sense, some technical sense, in which Hamiltonian simulation is like a universal problem that encompasses all of quantum computing. So therefore, if you believe there's a speedup for Shor's algorithm or one of these other sorts of algorithms, then you believe that there is an exponential speedup for Hamiltonian simulation as well. Now, the original Hamiltonian simulations, algorithms that were put forward in the 1990s, were very far out of reach of near-term quantum computers. One reason, kind of technical reason that this happened, is that their error scaling was very poor. So you would need a lot of qubits or a lot of time steps in order to accurately simulate your quantum chemical system. But what's happened within the last 5 years or so is there's been a huge amount of progress in making these Hamiltonian simulation algorithms more efficient, especially in the precision component of this. There have actually been exponential improvements in the precision parameters of Hamiltonian simulation algorithms. Now, unfortunately, these algorithms are still out of reach for near-term devices, but because of these kind of improvements, there is kind of a sentiment in the field that these Hamiltonian simulation algorithms, even though they are kind of long-term or far-term algorithms, they might be a bit closer than some other fault-tolerant algorithms that you might have heard of, like Grover's algorithm or Shor's algorithm, which we think are possibly even further in the future than Hamiltonian simulation. Great. Now, the second algorithm that I'll cover is a very different one, something called the variational quantum eigensolver, or VQE algorithm. And this algorithm solves a very different problem than Hamiltonian simulation. Namely, what it does is it tries to find the ground state of a quantum system. So you can think of this, if you're thinking of this analogy to classical mechanics and building a bridge, the ground state of the quantum system is what's the state it settles into after a long period of time. Like if you were designing a bridge, it would be, what's the curvature of the bridge at rest, without it being disturbed. And it turns out that finding the ground states of quantum systems is very useful chemically, because these are the systems, the ground states are the states that these systems tend to equilibrate to after a long period of time. So these are kind of equilibrium states of quantum systems. And these are useful for many problems in quantum chemistry. The basic idea of the algorithm is to kind of use a fusion of quantum computing and classical computing in order to find these ground states. So the basic idea is that you make an intelligent guess, or sometimes called an ansatz, of what you think the ground state of your quantum system will look like. And this usually involves kind of deep knowledge of quantum chemistry in order to make this ansatz intelligently. And then what you then do is you just try that guess using a quantum computer. And because this problem is a kind of natively quantum problem, the quantum computer can very efficiently estimate the energy of that state that you guessed. The basic idea is then that you can use the classical computer to iteratively refine this guess, and in tandem with the quantum computer, find a state that's very low energy in the system. So you can kind of see this problem as offloading some of the quantum computation to a classical computer. So all of the optimization part is done on the classical computer, and the only thing that you use the quantum computer for is really the core part of the chemistry problem, which is simulating the system itself and approximating its ground state energy. And there's also a lot of, you can also see this as somewhat offloading the problem to this ansatz as well. So it's kind of important to have a deep knowledge of quantum chemistry in order to run this algorithm. Now, VQE is a heuristic algorithm. So that means it does not have any performance guarantees that we know how to prove. But there is hope for speed up here. And the intuition is something like this. So we actually know that the general problem VQE solves is very difficult from a theoretical perspective. It's something called NP-hard for those of you who are familiar with the P versus NP problem. And what this means is that we would expect this VQE algorithm to fail on certain artificially constructed instances of the problem. So VQE is not a silver bullet that can kind of solve for the ground state of any artificial system that you construct. But on the other hand, there's intuition that it should perform much better on kind of natural instances of the problem that arise in practice. And the intuition given here is usually something like this, like if nature can find the ground state of this system, well then your quantum computer should be able to do so as well. So in other words, the intuition is that these kind of natural systems don't obey these kind of artificial complexity theoretic barriers that can occur if you look at what happens on artificial or worst case instances. Now, improving VQE is an extremely active area of research. The kind of key to improvements are choosing the right ansatz for this ground state, choosing a very efficient embedding of your problem into the qubits that you have at your disposal, and also compressing the problem such that kind of just the key quantum part is run on the quantum computer. So rather than kind of naively simulating maybe your whole system, maybe there's only some kind of small core part of your quantum system that you need to simulate, and by compressing it down to that, you can maybe try to fit the problem on a smaller size quantum computer. And again, the reason people are very interested in this algorithm is that it's a heuristic that might be implementable. We'll have to run it on real-world examples in order to judge its performance. So just to kind of summarize this portion of the talk, the basic landscape of quantum chemistry algorithms is there's Hamiltonian simulation algorithms for dynamics, which would require a large number of qubits, maybe less than Shor's algorithm, but still a large number. These have provable exponential speedups. On the other hand, there's this VQE algorithm that finds approximate ground states. It's a heuristic. We don't know what the speedups will be, but it can run on relatively small-sized quantum computers. So it'll be very interesting to see in the coming years how this algorithm performs. All right, so I'm now just going to very quickly wrap up my talk. So what I've tried to convey in this talk is that there are many different types of quantum algorithms with differing types of speedups. The near-term algorithms that we have at our disposal are all heuristic, but in the long term, we do know that there are provable algorithms out there which we know will have very large performance improvements over classical computing. So a major open problem of the field is therefore to ask, can we prove speedups for these near-term algorithms? Or maybe more realistically, can we prove speedups for medium-term algorithms? So can we take these algorithms for which we have provable speedups and kind of reduce the hardware requirements that we would need to run them, such that as hardware improves, we'll try to meet them in the middle. So this is kind of the major algorithmic challenge that we have in the quantum computing space. And I've told you about the most prominent near-term algorithms of QAOA and VQE. And the challenge that we're going to face in the near term is to try to understand under what conditions these algorithms give speedups. It could, in some situations, they could give speedups, in some they might not. So it'll be very interesting to see the performance of these algorithms on actual hardware. All right, that's it. Thank you very much for your attention. Cool. Sure. Great. So I have time to take one question, apparently. So yes.
I'll talk loud. So when you, okay, I'll use a mic. Maybe. Is it on? There it is.
Yeah.
So when you're talking about the evolution, and as the researchers and academics are working on these algorithms,
yes.
What's the challenge there? Is it that just it's pure science, it's new space? Or are there material needs that the researchers have? Do they need data sets? Do they need access to specific spaces to validate these heuristics and then improve them?
Sure. So I'd say that's a great question. So in the heuristic space, which is where a lot of the industry is happening, there is a need for real data to run these algorithms on because they're heuristic algorithms, that's the way you judge their performance, because you don't have any mathematical, you usually only have very limited mathematical insight into the performance. On the other hand, in terms of what's the barrier to improving the performance of these kind of longer term algorithms with provable speedups, there I see the barrier just being that there are very few people in the world who have a training in quantum algorithms, because it's an entirely new space. And if you have a PhD in quantum algorithms now, you have to have started studying this well before it looked like these quantum hardware platforms would come online, right? So I think there it's more of a manpower challenge, and it's important that we kind of train the next generation of computer scientists to have these quantum algorithm skills so that they can help us develop this area.